noise as well. Can we just lower the screen by like an inch or so? Oh, well, maybe a little further. There you go. That looks good. All right. So this is a presentation I gave just last week at the conference in Europe on text search and pattern matching. The gist of it is that there's a lot of different ways that you can do pattern matching in Postgres, and usually what you want to do is use the simplest method that'll meet your needs. So there's kind of this whole spectrum of really simple ways to do pattern matching to really complex ways to do pattern matching. Generally speaking, the simplest method is going to be the fastest and obviously the easiest. So that's what you're going to want to do. There are cases where you actually have to combine more than one method. We'll talk a little bit about some of that later, but usually when it involves some combination of fuzzy matching with other things. So I'm going to cover a summary of the methods and then kind of give you an overview of each of the methods and then go through a handful of example use cases. Just some caveats. I'm going to cover full text search in here because Postgres has it, but you could easily do a full day class on full text search in Postgres. There's a lot to it. It's very customizable. I'm just going to kind of cover the basics, enough to make you dangerous probably. And even some of the other things that we're going to talk about, I'm just going to kind of cover at a high level, especially like regex is another thing that you could probably, if you just wanted to learn everything there is to know about, or forget about everything there is to know about, just even a lot of what there is to know about regex, you could probably spend days. And I'm not going to try and do that. And then finally, the other thing is that much of what I'm going to cover, at least when I get down to the examples, is how do you do fast pattern matching with case-insensitive searches. And that's something that's not, there are definitely ways to do it, which I'll cover. The standard methods don't work well with that, but there is an extension to Postgres called CI text that ships with it. And the CI and CI text stands for case-insensitive. So that data type, by its very nature, is case-insensitive. So that's actually another way you can sort of facilitate case-insensitive searches, but I don't really cover that in this talk. So in terms of the things that are covered, there's standard method. Pretty much everyone who knows anything about SQL has probably used like. There's actually something called similar to, which is similar to like, but also similar to regular expressions. And then Postgres supports POSIX style regular expressions, which is, I don't know if that's still completely unique amongst databases, but it's fairly unique. Does Oracle, for instance?
I don't know that.
I don't.
When you say POSIX style, is that different than PCRE?
Well, PCRE is POSIX style. There are several kind of flavors of regex. PCRE, there's actually different levels of the Perl compatibility. There's Python style, that's a little bit different. There's basically, I think the regular expression engine that was built into Postgres was written by the guy, it was written by the guy who wrote it for Tickle. So it actually is the Tickle regular expression engine, which has been kind of lifted out and plunked into Postgres. I'm also going to cover some Postgres extensions. Fuzzy string match has got 4 different methods for doing fuzzy matching. So we'll go through how those work quickly. Soundex, Levenstein, Metaphone, and double Metaphone. And then this other extension, Trigram, or PGTRGM, which is hard to say 10 times fast. I'm just going to call it Trigram matching. That extension is really interesting because one of the things it provides are some extra methods for indexes, which end up being useful for a lot of the other stuff. as we'll see when we get down to the examples. And then finally, I will cover, like I said, at a high level at least, how full text search works in Postgres. The sample data that's used throughout this presentation is actually a table called messages. This is just a subset of the columns, but these are the most important ones that I'm using in this example. It's got a from column. It's basically email messages, a from, a to, a subject, a body, and then this FTI field is of this type TS vector, which we'll talk about later. But that's used for full text search. And this data actually is the data that comes from the Postgres mailing list archives. So it goes back quite a number of years. There's over 1 million messages in it. So it's not a huge data set, but it's a pretty significant and a real life data set that the examples are based on. So now we'll dive into the overview of each of the different methods that we've got. Like is an expression that returns true if the string matches the pattern. It's typically, the string typically comes from a table in your from clause, but doesn't have to. It could be any string. And it's usually used as a predicate in a where clause, so it's a filtering criteria. If you use the keyword like, that is case-sensitive search in Postgres. Unlike some other databases, SQL Server, for instance, I think by default on Windows, at least it used to be case-insensitive. Oracle, on the other hand, is typically case-sensitive, at least on Unix and Linux. I'm not sure what they did on Windows, actually.
Case-sensitive.
It was case-sensitive also. So depending on the database you're used to, if you're not used to Postgres, you might find differences from database to database in terms of that. But Postgres also supports an ILIKE, which is a case-insensitive like operation. The trick with that is to get it to use an index, which we'll cover. This is the syntax for it. You say string, like, some pattern, and then there's an optional escape clause because the pattern can include escape characters in order to escape the wildcard characters. This double tilde is actually exactly the same. This operator is exactly the same meaning as like. And then I like, you've got this double tilde asterisk, which is the same as I like. But you can see the syntax is basically the same. And then an alternative to I like is to use a function like lower over the string and then compare it to a pattern that has been forced to lowercase as well. And again, I'll show you examples of how that can be used to speed up searches that are case insensitive. If you need to negate a like, use the not keyword. And then there's also operators for that. So you can say string not like pattern, or you can say string and then instead of just the two tildes, you'd have the exclamation point in front of it, which means not. Or string not I like. Same thing with that pattern. Or you can, because these expressions just return a Boolean result, you can also basically wrap the entire expression in parentheses and then put a not outside, which will negate the whole expression. So that has the same effect. Wildcards and like, again, you're probably familiar with this, but we'll go over it quickly. An underscore matches any single character, and a percent matches 0 or more characters. If there's no wildcards, the expression is more or less equivalent to an equals. Someone pointed out in my talk that it's not semantically exactly the same as equals, but for most intents and purposes, it's effectively the same. If you need to match the wildcard characters themselves, then they have to be escaped. And the default escape character is the backslash. But let's say you're trying to match backslashes, you don't want to be doubling up backslashes all over the place. You can change that with the escape clause. And again, whatever the escape character is, you can match it by doubling it up. One of the important things, if you want to make like queries fast, is the idea of these index operator classes. When you create an index using the standard syntax, and don't specify basically anything, you just say create some index name, on a table, parentheses, column. By default, you're going to get a B-tree index, which is a normal index. If your database is using the C locale, and you have an anchored pattern, which means you've got some set of characters and then a wildcard %, then that normal B-tree index can be used. But 10, 15 years ago, that was pretty common that people built their databases with C locale, which is just basically ASCII characters. These days, almost everyone uses UTF-8 in order to support multilingual type operations. And if you're using something other than the C locale, those anchored patterns cannot use the standard B-tree index. So the solution to that is to build the index with these alternate op classes in it. There'll be examples of that later in the talk, how to do that exactly. You might also want to create the normal B-tree index on the same exact column though, because if you've got other queries that are using less than equal to, greater than, or greater than or equal to, those queries would use the normal index. So you might end up with two indexes on the same column, one with the special pattern ops and one with just the normal B-tree. And one of the problems with this is it does not work for ILIKE or the equivalent operator. And the solution, as we'll see later, is that you can create an expressional index over the function lower on the column, or you can use this extension Trigram, which has special operator class. Just an example of a like clause with an escape clause, since it's not actually all that common in my experience. If your pattern has some backslashes in it already, you might want to change the escape to something else, some other character, and then you can use that to escape the special characters underscore and %. So in this case, this pattern is going to match this string, which has all of these literal characters embedded in it. Okay, so now we're done with like, and we're going to move on to the next one. Any questions about how like is used? Like I said, that one's the most common of all these things, so probably all pretty familiar with it. Similar to is equivalent to like, but it uses, it has like an extension to it that makes it also in some ways similar to regex. So it kind of borrows some ideas from regex. It looks very much the same, string similar to pattern with an optional escape clause, or string not similar to some pattern. The wildcards that you use in similar to are exactly the same as like, but it also supports meta characters that are borrowed from the regular expressions. So in other words, you can use a pipe, and that means I want either of these two alternatives. You can use an asterisk, which means you're repeating the previous thing greater than or equal to 0 times. So it doesn't have to, it's optional, but it can repeat many times. A plus means it has to be greater than or equal to 1 time, so it has to at least exist once. A question mark, which basically means it's optional, it can exist or not exist. And then you can also specify it needs to repeat an exact number of times, or greater than a certain number of times, or between a certain number and another number of times. And then you can use parentheses for grouping. So if you're any experience with regex, you'll probably recognize these things from regex. It doesn't support all the other stuff that regex supports.
But supports the most common.
Right. So these are just some examples. If I want to say that this is similar to that, this is really no different than using a like. Just using like here in this case. In this case, I'm saying that it could either be a capital C or a lowercase c, and so that is going to match because I've got a capital C in that position. In this case, I'm saying that this C here has to repeat 4 times, but it only repeats 3 times, so that one's going to return false. And here I'm saying it's got to repeat 3 times, and so it does. That's true. And then here I'm saying that the C and the D are optional, in which case that's true. So now the third major built-in type is the regular expression syntax. Again, it works, similar to the like and I like, but one difference here is that the pattern that you've got can match anywhere within the string, similar to the way a regex works, unless you specifically anchor the regex with a caret or a $sign meaning the beginning or the end of the string. And it interprets the pattern using POSIX definition. So POSIX defines a number of things in a specific way, and this is going to adhere to the POSIX definition. So the operator for that is just a single tilde. So a string tilde pattern will match a regular expression, and that form is case sensitive. If you have string with a tilde and an asterisk, that's actually a case insensitive match. And then if you put the exclamation point in front of the pattern, then that means it should not match. Or in other words, it'll return true if it does not match. And there's a case sensitive and a case insensitive version of that. So, as I said earlier, regular expressions can get almost infinitely complex. I'm not going to try and cover all of that. I provided the link here into the documentation that covers it in a bit more detail. Books have been written on regular expressions and so on. So we're not going to try and go through all that. But here are some more examples of patterns that match regular expressions, and whether they should be true or not, I've kind of indicated by the name of the column. Any questions about any of these? So one of the challenges with the regular expression is that without an index, that's going to be pretty slow. So I do this search, just finding the date from messages where the body matches this for multi-transact. almost 27 seconds. Using the trigram, which I haven't really gotten to yet, but if you create the index, here's the first example of creating an index using a special type of operation instead of the normal B tree. So if you say create index, you give it any name you want to give it on the table using gin. So this is a special type of index on the column body type using gin trigram ops. So this is provided by that trigram extension. And now when I run that same query, you can see it uses a bitmap index scan, and now the query is running in a little bit less than 200 milliseconds, down from 26 seconds. So that's not bad. It's pretty good. There's also a trigram gist index. So if you create the index this way, using gist, just trigram ops. In this particular case, trying to index that body, which can be very large text fields, it just actually throws an error because it won't fit on the Postgres page size. could run into that with gist. And for the sake of comparison, again, I'll cover full text search later, but if you have the proper things done for full text search and you do what is essentially the same query using full text search, it finishes in 22 milliseconds instead of 200 milliseconds. So in this case, trying to basically pull this word out of a fairly large field from a lot of messages, full text search was actually really efficient. They're both pretty quick, maybe quick enough. Maybe quick enough that you don't want to bother with all the complexities of the full text search, but the full text search is faster.
Question. When Postgres builds its indexes, when you create the index, does that start building and wait for the index to finish creation before it moves on? Or does it build in the background?
It does not build in the background. So when you run a query that says like create index, it'll sit there and hammer away at it, and basically that session is blocked until the index is finished being built. The other thing is, if you do not build, there's a syntax for building and create index concurrently, which will allow concurrent writes to occur. But if you're just building a normal an index without the concurrently keyword, it'll actually block all writes on the table. It won't block reads.
Yeah, reads are not blocked.
Yeah, reads are not blocked, but it will block writes. And so if you've got,
Live table.
if you got a live production system and you got to build an index on a really large table, and it's going to take the index an hour to build,
Yeah.
you'd be blocking potentially all the writes to that table for that hour.
But when you use concurrent, it may take 2 hours to build.
Exactly. So if you use concurrently, it won't block the concurrent writes,
It'll take longer.
but it'll take longer to
But
build.
you can still use it. Okay.
Basically what it does, if you do concurrently, it builds like an extra copy of the index off to the side. And when it's all done, it like does the necessary, it locks just long enough to kind of like move it into place. Whereas if you're building it without concurrently, it's really got to lock the table with a certain level of lock for that entire time. Concurrently, the reason it takes longer is it actually makes 2 passes.
So any test to pick any updates that
Yeah,
happened
basically any
since it
updates that
started
came in
the
since it
second
started,
phase.
it gets in that second pass. So now we're going to move on to the fuzzy search methods. These next 4 are all installed with the extension fuzzy string match. I don't have it on this slide, I probably should. The syntax is just create extension fuzzy string match, assuming that you've actually got the binary packages installed for that. If you're installing from RPMs, I think there's a PostgreSQL -contrib RPM that would need to be installed. On Debian, I think it's probably something similar on like Ubuntu or Debian or Linux Mint. As long as those are installed, or if you're building from source, you would have to compile it and do make install. As long as those are available on the system, then a create extension fuzzy string match will make these functions available for you. Soundex is kind of an old algorithm. It was originally designed to find names that sounded alike, and it's really based on, I think, English names, so for English-speaking countries. So it tends to work better for English names. But you can see here, if you do Soundex on the name Joseph and Soundex on Joseph spelled phonetically, and you can also, with the Soundex function, also comes this difference function, which is a little bit of a misnomer because what it's telling you is how many of the positions are the same. Soundex will always produce this 4-character code, and the difference, if all 4-character matches, will be 4, and if none of them match, it'll be 0. So you can use that to say, how closely matched are these 2 names, essentially. And you can, there's no reason you can't use it on words other than names, but as I said, it was originally kind of defined to developed for that purpose, I think. Levenstein is an algorithm that is looking for the differences in basically on a character by character basis. So it's computing a numeric value that is supposed to indicate how far apart these two words are in terms of the characters. So if we do Levenstein over Joseph and Joseph, it gives 2 because not only is it a different length, but this character here doesn't match. Whereas these two words are both the same length, and the only character difference is this third position, so you get a 1. And if you do foo and foo, there's obviously no difference, so you're going to get a 0. So this gives you an indication of how far different these two words are. It is case-sensitive comparison, and the inputs are limited to 255 bytes max. I think there was some discussion about removing that limitation, but I'm not sure. I don't believe that's been changed as of yet in Postgres. This other algorithm, Metaphone, it makes a code for an input string. It's insensitive in the way it works. It's still limited to 255 bytes, but it takes another argument that lets you set how long the output code should be, which kind of allows you to adjust the sensitivity for how close you want to make the match. So if you take these two words, extensive and exhaustive, and you say, give me 6 characters, you can see that the codes are slightly different. But if you move them down to 3 characters, and you can see I've messed with the case here, but in that case, they both produce exactly the same code. So I could say that these two words using a 3-character code are the same, but using 6, they're not. And you could also kind of envision the possibility of using Metaphone with maybe 6 or 8 characters of the code output, and then layering Levenstein on top of this to see how many of the positions of the output code are different. And then there's another algorithm called double Metaphone, which actually computes a primary and an alternate code. There's 2 different codes it'll produce. The non-English names, especially the primary and the alternate algorithm, can produce different codes. And but this one it's insensitive, but there's no length limit on the input string, so it may be useful from that standpoint. You don't have the ability to tell it how long the output should be, though. So in this case, extensive and exhaustive are going to produce slightly different codes. And this word Magnus is actually a name, the name of a friend of mine from Sweden. And if you look at the D Metaphone and the D Metaphone alt, you can see that it produces different outputs with that same name. Okay, so then the other extension for fuzzy matching is this Trigram extension. It gives you functions and operators for determining similarity. What it is basically, it takes a string and it breaks it down into groups of 3 consecutive characters in the string, and then it looks at the 2 strings and it sees how many of those groups of 3 actually match, and then it bases its calculation of similarity on that. It also provides these index operator classes that I talked about earlier that can help speed searches. And those operator classes are supported for like and I like queries. And the comparisons are case-insensitive. So this extension is actually really useful if you want to do like, case-insensitive, and also some other things I'll show you later in terms of non-anchored patterns, and you want it to be able to use an index and run fast. this extension is really useful for that. So here's an example. It comes with this function setLimit. So setLimit is going to control the limit at which the similarity function is going to return, or I should say the similarity operator that it provides is going to return true. So this operator in the where clause is going to return true for the rows that it deems are similar enough, and the adjustment on what is similar enough is done through this other function. As I noted here in the comment, it defaults to a 0.3, and in this case I changed it to a 0.6 in order to filter the results. So when I run this query, select distinct from the similarity function that's provided by this will give me the actually calculated number that similarity came up with, and this operator is doing the same calculation and producing a true for the ones that are similar enough to match what I set up here. So by doing the similarity in the target list and then using the operator, I can actually see what similarity was calculated by the operator. So here I'm searching on Joseph Conway spelled in kind of a strange phonetic way, and you can see that it actually did a pretty good job of, even found a really old email address of mine from like 1999 or something like that, based on kind of a phonetic match. And I used my own name and email address in these examples, not so much because I'm vain, but because I didn't want to use anyone else's email address on slides that were going to be made available publicly. They may not be real happy with me if I did that. Fortunately or unfortunately, I've been on the mailing list for Postgres for so many years that I get an absolute ton of spam every day, and I've got really good spam filters. So at this point, making my email available probably doesn't make that much worse. Okay, so now we're on to full text search. Any questions about the fuzzy string matching stuff? So, kind of as an overview, full text search lets you search documents with potentially complex criteria. It's better than other methods that we've talked about because it does offer linguistic support for derived words. In other words, it'll do what's called stemming. It'll take words that are equivalent and make them equivalent for the purposes of the search. So, things like removing the S from something that makes it a plural, or the ing, or different versions effectively of the same word. That's what stemming does. It'll remove the stop words. So normal stop words are things like and, those kinds of things. That'll remove them from consideration. There are functions available for doing ranking by relevance. So somewhat like what we just saw with the similarity, it will do a calculation on relevance of the result to the pattern that you're trying to match, and then it provides a functionality for you to do ranking on those, and we'll show those, at least an example of that. And it does very flexibly use these special gist and gin index. It is a very complex topic. I've given you links to some of the main things in the documentation. You can do things like it makes use of what's dictionaries for some of what it does. Postgres ships with some standard dictionaries, but you can actually create your own custom dictionaries to make special stop words or special types of stemming that don't exist outside of your application. When you use full text search, you typically want to do pre-processing on the strings that you're searching on. So the way that works is you convert the text into what's called this TS vector. It's a special data type. You store that TS vector in a column, and then you build an index on that TS vector column. So on that messages table that I showed you before, there's a trigger that has been created on the table, so that every time on an insert or an update to either the subject or the body text field on that table for each row, we're going to execute this procedure, and that procedure is right here. And you can see in that procedure we're going to take the subject and the body text. We're doing a coalesce, which will mean if either of those is null, we're just going to make it an empty string. We're applying a weight. We're first converting it to a TS vector, and then we're going to apply a weight to it, and then we're going to concatenate those two things together. So I'll explain a little bit of this on the weighting further on in the slides. But basically the weighting can be used so that when you do relevance ranking, you can let certain parts have more effectiveness or more weight on the relevance ranking than other parts. The idea being that if you've got, if you're searching for a word in the subject and the body, it probably is more important if that word exists in the subject than if it were, if the word exists somewhere in a very large body of text. Another example of that is like the title of, say, a document. You might have a title and an abstract in a book. And if the word exists in the title, that's probably really important for your matching. Whereas if the word exists somewhere in the book, it may not be as important.
On that trigger, when it says for each row, is that every row already in the table, or every row that's being inserted or updated?
Every row that's being inserted or updated. So anytime someone does an insert or update operation, that can affect obviously many rows. And this trigger will fire for each row. There's also you can say for each statement, which will mean the trigger will fire once for the entire statement. But you cannot do any modification of the rows if you have a statement level trigger. In this case, we want to modify those rows because we want to populate that FTI, the TS vector field, with the result of this calculation. And then, of course, we're going to build that index. So just like we saw before, more or less, we're going to build an index. You'd give it some name on that table using gin on that column, the TS vector column, and it'll use the gin operator type. Raining hard in San Diego. May not be a fun drive home. And thunder and lightning, we should hardly ever hear.
Was the forecast?
Yeah.
Never, right?
So a little bit more on the weighting. Weights are used in the relevance ranking. It's basically an array. There's a default values for that array. So there's a D, a C, a B, and an A weight. You can see the A weight is 1 in the default, and the D weight is 0.1 in the default. That means whatever is matched to the A has 10 times the effect as whatever matches to the D. And if we go back to here, you'll see that the subject I've said is an A weight, and the body is a D. So that's how I'm saying that matches in the subject are more important. But I can actually change the default weights to something else if I need to. The way a TS vector is created is basically the string is parsed into individual tokens, which effectively means words. So it's split up on the spaces. You can have different classes of tokens that are processed differently, but Postgres has a standard parser with a predefined set of classes in it, but you can customize that. So again, that's beyond the scope of this talk, but it is completely possible to come up with your own methods for parsing. Those tokens are then converted into lexemes. That's where this stemming that I was talking about comes into play. So the tokens that it parses out of that text can then be converted into a a different kind of normalized token, which is called a lexeme. Again, this uses dictionaries, but you can create your own custom ones. And some of the things that happen when you normalize, everything gets folded to lowercase, so that's what makes it case insensitive. Suffixes get removed from words. Stop words are eliminated. So now the other half of the equation, we take the string that we want to match against, we're going to convert it into this tsquery. But the pattern that we want to match against, excuse me, we took our string and we turned it into a ts vector. The pattern that we want to match against has to be converted into a tsquery. And in that query, we're going to use, again, lexemes, but we can combine them now with Boolean operators, and or not. So ampersand, the operators that you would probably expect are used for and or not. The not is going to bind most tightly, so if there's a not next to something, it means not that, rather than not, this and the next thing. And is going to bind more tightly than or. So if I haven't specified using parentheses how the operator should be combined, then the and is going to, if I say this and that or something else, I'm first going to do the and then I'm going to or the two things together. This would have been more appropriate for Halloween, right? And the other thing that you can do is you can use an asterisk. I'll show you an example of that on your lexeme in the query that is going to specify I want to do prefix matching, kind of like that anchored pattern matching that we were talking about earlier. Or I can use weight labels. So there's a function called toTSQuery. You can also cast a string directly to tsquery, but if you cast it, it'll only work with simple strings, and it doesn't support the Boolean operators or the weight labels or the prefix match labels if you do the casting. But if you use the function, it does support all that stuff. So if I take this string, hello and world or foobar, then it means I want to match something that has both of these words or has this word. And this other string, Postgres : with an asterisk, is going to get converted into something that's matching basically the prefix POSTGR.
So that second example is the casting. With is that what that is? Okay. So when you cast it that way, is that an example of it removing a suffix with how it only has that?
Yeah, I'm actually thinking that I got this slide wrong. I think it does support that because this is a prefix match. What you'll see in this next example, there's this plain to tsquery, and with plain to tsquery, it loses that entirely. So I need to go back and look at these slides. The other thing that's important to note here is that if you use this plain to tsquery, even though it looks like I'm using the same operators in this case, and using the prefix matching, using the plain to tsquery, that gets stripped off, so I don't end up with the prefix matching here. And these words, even though I've said and here and or there, it's just this and that, because all it's dealing with are the words. It basically pulls the strings out and then just combines them all with the and operator if you use that. So the way you do matching with text search is this double at operator. it returns true if the TS vector, which is your preprocessed document, matches your tsquery, which is your preprocessed search pattern. And it doesn't matter which one you put on which side. So in this case, what I'm showing here is my TS vector column, FTI, add, and I'm saying find me if the word multi-exact in the subject and race in the body and bug in the body. And it comes up with 3 messages. And the only reason for this part up here is just to make sure I'm not showing these guys email addresses.
So one of the things with the you said pre-processed search query. So I see how this working go. So with that, you can kind of save, for example, somebody's search query, and then later pull that out.
You could use to tsquery function on the string that they provide, save that in a table somewhere, and then match against it. Sure.
Is that the typical use case for processing?
I wouldn't say people typically save the query like that. You usually just save the TS vector, because that's the body of the document or whatever that you're searching against. But I don't think there's any reason why you couldn't save the query if you wanted to. It doesn't probably save you a whole lot of time on the query speed, because typically the pattern you're matching against is fairly short and simple.
Well, I was thinking more of so we have, for example, systems people making the same restrictions in an interface.
Yeah, read it repeatedly. You don't want to have to remember
right.
it.
So then if we could do a safe search for that and actually take the generated query and save that, and they can give it a name, and then later they can just reapply that same thing.
Yeah, sure. In terms of relevance ranking, there's these 2 functions available, tsrank and tsrankcd. Tsrank is purely going to be based on the frequency of the matching lexemes. tsrankcd is actually going to take the proximity of the lexemes into consideration. So you'll get a higher relevancy rank if the words are closer together in the document, the ones that you're searching for. One of the things that you find, if you're going to use this, you need your query as an input both to the operator as well as to the tsrank function. So if you don't want to have to basically parse that query string more than once, one way to do it is to use a CTE, common table expression, and put that creation as effectively the TS query in there, and then you just use that reference in both places. So that's what I've done here. And this is the way by calculating TS rank, and then you can use that as what you order by in order to just grab the most relevant items. So if you want to find the top 10 items in terms of relevance or something like that. There's also this TS headline that is available to you. You can use that to basically highlight the search terms in the document. It's going to return an excerpt with the query terms highlighted. This is a fairly, at least from my experience, is a fairly expensive function, so you wouldn't want to run that on every row prior to filtering. So in this case, what I did was I wrote this query as basically an inner query and an outer query. And then in the inner query, I do the search like I was doing in the last one with the CTE to create my query and the rank inside of here so that I could limit the number of values being returned to 4. And then in the outer query, I'm actually using the headline function on what got returned by these inner queries. So I'm basically just going to apply that headline to the top 4 items that I returned. see how that works. The subject was, this, is anyone aware of data loss causing multi-transact bugs in 932? The rank was very high, and then the headline just shows you, the keywords being bolded, basically using HTML. And this first part up until the semicolon here is actually in the subject, and then the second part is the coming from the body. So now we're down to the example use cases. Any questions with anything prior before I jump into this? Okay. So I'm going to go through an example of an equal, an anchored, a case-insensitive anchored, a reverse anchored case-insensitive, an unanchored case-insensitive, and then a fuzzy match and a complex search with relevancy ranking. So basically starting simple and moving on to the more complex stuff. So if I want to find all the rows where a column matches a pattern, really your best, what you should use is just the equal operator. If you run that query with no index at all, in this case it's actually still not terribly slow, it's only half a second. But you can see it does a sequential scan on the table. Now if I build just a standard index and I do the equal search, it uses my index, and you can see it's lightning fast. This is less than a millisecond, it's 161 microseconds. So this is really fast. Now if we want to do what's called an anchored search, so this is where we've got a pattern and then our wildcard at the end of it. A like operator is really, with an index, a suitable index is your best option. If I create that normal index that I had before, and I try and run this like query with the anchored pattern, you notice it still does a sequential scan. And that goes back to what I was talking about earlier with those special type of index operators for patterns in a multi-byte database. So it still did a sequential scan, it still took half a second. But now if I go back and recreate this index using text pattern ops, do the same anchored query, it returns almost as fast as my equal query did. It's 133 microseconds, so really fast. So now what happens if I want to do an anchored case-insensitive query? So I want to find all the rows where I matched a pattern wildcard, but in a case-insensitive way. At this point, one good way to do this is using the like operator, but building what's called an expressional index. Are you familiar with expression indexes in Postgres? So when you create an index, you can actually say, I want to create an index, give it a name on this table, and then instead of just using the column name in here, I can say, I want to execute this function over this column, or in other words, I can write an expression in here. And then furthermore, I'm going to say use my text pattern ops still. So now when I write my query, I can say where the lower over that column is like some pattern which is already lowered, or more likely what you would do is you take probably some input from a user interface, and then you would lowercase that search pattern before you stuck it into the query here. And
Do you have to, the column you're comparing against, do you still have to do the lower vel so that it uses the correct index?
yes, you do. So it'll detect the fact that your index is created on the lower of that column, and then this is the same expression, so it knows it can use that index. So in this case, it will use that index, and again, it's slower than the previous one, but it's still pretty fast. It's about a quarter of a millisecond, or 258 microseconds. Remember some of the examples that I went through earlier. We were talking about 20 milliseconds, 200 milliseconds. This is like order of magnitude, a couple orders of magnitude faster than the 200 milliseconds. Now here's a case where, since I'm trying to do anchored and case insensitive, I can also use this trigram gin index with the ILIKE. Because remember, ILIKE is case insensitive, and that index type that trigram gives us actually can be used for an ILIKE query. So if I create that, this is the syntax finally for creating an extension. So create extension PGMs for DRGM, and then I create the index on messages using gin on that column, gin trigram ops. So now I don't have to apply lower to this. I can simply say that column is ILIKE this search pattern, and it'll use my index. But now we're talking about 93 milliseconds instead of microseconds. So for a lot of use cases, and it's certainly better than a sequential scan, but it's not nearly as fast as building that expression index over lower on the column. And you can also do this trigram provides you with this gist index type, so you can build that index, and you can see in this case the gist index is slightly faster than the gin index was. It's actually almost twice as fast in this particular case.
So when you were talking about the gist index before, you mentioned the page size.
Which can be a problem with the gist index.
Is it is there really a benefit to using the gist index? Well, what would be the benefit? Why would you choose to use that over the other one?
In general, gist indexes, there's some guidance in the Postgres docs about this, and it's actually changed a fair bit over the last several releases, but in general, gist indexes are considered to be smaller, faster to build and maintain, but for a lot of use cases, typically slower when you're doing a read-only query. But here clearly is an example of one where the gist index was actually faster even for reading than gin was. Gin indexes tend to be larger, so larger footprint on disk. They tend to be slower to build and more overhead to maintain, but faster when you run queries. But again, those, like I said, those are generalizations. And gin indexes have been improved quite a bit over the last couple of releases, and they keep getting better and better. So I think actually the latest guidance on the latest version of Postgres is now that for full text search, for instance, gin indexes are usually preferred over gist indexes. But I guess one of the things and you'll see that as we go through here, which one is faster is sort of context dependent. So my feeling is you probably want to test both in your environment and just see which one performs better.
I mean, if you did think that a gist index was performing better for whatever reason, but you're getting to the point where page size was becoming an issue, would it be acceptable to increase the page size?
That's not, it's something that you can do, but almost nobody does, and it has to be done at compile time. So if you were to do that, you would end up running kind of a non-standard Postgres instance that would be more or less unlike everyone else in the world who's running Postgres. And so although theoretically it should work, but you could run into bugs that nobody else runs into, potentially. So I think, generally speaking, you wouldn't want to do that.
Yeah.
If you had some proprietary product that you were building on top of Postgres, and for some reason it made sense to change the page size, and you've got your own engineering department that's going to go through and help debug issues that you run into, then it might make sense to do that. But I definitely wouldn't recommend that as a general recommendation. Okay, so now we have a case where we want to find something that matches a wildcard and then the pattern. So this is a reverse anchored case. We still want it to be case insensitive. This is another case where you can actually build an expression index. You can build an index on lower over the reverse of that column, because reverse is another function that's available to you. Again, we're still going to use the text pattern ops index type. And now when we do the search, we're going to have to do lower reverse from, and we're also going to have to reverse our pattern. But when we do both of those things, you can see we get an index, we get use of the index, and it's actually not too bad. This one is less than 20 milliseconds. Again, we can also use the Trigram gin index here with ILIKE because it's case insensitive. This is the same syntax for building the index we saw before. Now we don't need all of that extra function wrapping. So we can just say where this column is ILIKE that pattern, and we'll get to use the index. But it's it's 4 times slower. Still not bad, 88 milliseconds. For some use cases, this might be perfectly adequate, and it's less complicated. So you'd have to judge for yourselves whether it makes sense to use this or use the other method. And you can also use a gist index again, Trigram gist index. Same benefit here in terms of simplifying the way the query is written. Again, in this case, it's a little bit faster. About 3 times slower than the other method instead of 4 times slower than the other method. So now we get to the case where we want to do what's called an unanchored pattern match. So this is the type of thing that you see people doing all the time. We say sum column like percent sum string percent, or ILIKE, where you want it to be insensitive, case insensitive. And using traditional methods, it's not possible to use an index. But again, this is where this Trigram indexing comes to the rescue. So there's no way to do that using the normal pattern ops index. If we don't have an index use, this query runs in about 2 seconds. Does a sequential scan over the table. But if I build the gin index and rerun that query, it completes in 30 milliseconds. And here's a case where now our gist index, it does use the index, but it's 150 milliseconds. So for whatever reason, the gin index is a lot faster than the gin index in this case. But I don't have those other alternatives in this. And this is a very common use case where people have some kind of a web search form. They want to be able to search on any of a number of different fields. They let people decide which fields they want to search on, and they cram the search term in between the wildcards and then just let the query go. And using the normal method, you can't use an index, but using the Trigram extension, you can. So now this is our fuzzy matching example. I want to match all the rows where I'm matching a column, but in some kind of an inexact way. In this example, I'm going to use the Metaphone function with an expression index. But you might also use Soundex or Relevance Ranking or Metaphone, or just plain Trigram, depending on your specific needs. Or you might use it, as I pointed out earlier, a combination of them. So create extension fuzzy string match. I'm going to create this index on the Metaphone function over that column. So similar to what we were doing with the lower, or reverse and lower. And now when I run the query on messages where Metaphone of from is equal to Metaphone of this phonetic spelling of my name, in this case, you'll see it will use the index. You can actually even see in this explain what the result of that calculated value was. And you can also see in here that in the actual, that it found 108 rows in the table that matched that Metaphone value. And it did it pretty quickly. 445 microseconds. So then, as we saw earlier in our full text search, we want to do complex multi-word searching, we want relevancy ranking. So in this case, I'm going to match against my TS vector column, where there was the word bug in the subject, and the words deadlock and startup in the body of the message. It'll use my index. It actually finds 2 rows. No, excuse me, 93 rows. That was the estimate, was 2. Finds 93 rows in the database that match these. So that must have been a fairly long thread. And it comes back in 12 milliseconds. But again, you notice the full text search ends up being on the order of tens of milliseconds. Some of these other methods were coming up in microseconds. If those other methods meet your needs, probably a good choice.
Is the full text search option the only one that supports data from multiple columns? I mean, obviously you
Directly, I mean, you could concatenate
Yeah.
multiple columns together and then match them against a pattern. In fact, that's fairly common. I've seen that where, you know, I want to take a search term from the user, and I want to find it in any of like 8 different columns in my table. So I might just take those columns and concatenate them all together, and then say that thing like percent search term percent, and the performance of that is probably horrible in most cases,
Yeah.
unless they actually thought to build
An
an
index
expressional
of-
index over that
of all of it.
concatenation. And actually even that wouldn't work with the unanchored pattern unless you have the Trigram extension installed. So yeah, that Trigram extension is really useful.
So I noticed when you're doing the weights and stuff for the full text search, it was A through D. Can that go higher? Can you use?
I believe it only supports 4 different weights. I could be wrong about that, but I think it just supports 4 weights. But yeah, I mean, if you think about it, that's, for a lot of use cases, is probably fine. You know, for most articles or something like that, you might have like an author, a title, an abstract, and a body.
Cool. Thank you.
Okay. Any other questions? Anything anyone want to talk about other than the presentation? Should we just call it a night and drive home in the rain? Yeah, actually, it does sound that way.
Cool, can't wait to play around with this. I started a online tutorial on Postgres with Python.
Oh yeah?
I forget where it's going to, but I just started doing it today. And I was thinking, this week I can use that with the tutorial. It's like using restaurant menus or something. So I was going to do the basic one and then kind of extend it with the text searching and compare how different things perform.
Sounds like good stuff. Okay. Well, I have not scheduled the next meeting yet. But what we've been trying to do is meet about every 2 months. And actually, I have been doing Tuesday. I guess we pretty much said we were going to try and do Tuesday nights, right? So we're trying to do a Tuesday night about every other month. At some point, maybe we'll start doing them more often than that, but at least for now, that seems to be working fairly well for everyone. So hopefully you'll come back to the next one.
Yeah.
Hopefully the next time it won't be raining, we'll get more people to show up.
Yeah.
No, next time it'll be January, so that's all winter.
Yeah. Actually, that's a good point. In January, the third week of January, Thursday, Friday, Saturday, Sunday, is a conference in Los Angeles called Scale. And we have a 2 days of Postgres talks at Scale. I'm the organizer for that, or at least one of the organizers for it. So we'll actually do